Okay, guys, let's now talk about indeterminate powers. First, what are indeterminate powers? When you have one function in the power of another function, for example, f of x to the power of g of x. As x approaches a, which can also be infinity, and there are three special cases. You raise 0 to the power of 0, or you raise infinity to the power of 0, and you can raise 1 to the power of infinity. Let's kind of learn how to work with L'Hopital's rule if you do have powers and they are looking like one of this. Usually, guys, the general method is to use ln, like remember logarithmic differentiation. I'm going to do it once in general, but I think examples are much better explaining how to use it. So there are two ways to represent it. You can use either to write down way number one. Way number one. Let's consider y equals f to the power of g. And then take ln of y. What are we going to have? Remember, whenever we take ln, power goes in front. Or maybe I should write down ln first and then kind of do that. So ln f to the power of g, and we are going to have g of x multiplied by ln of x. So basically, if you take a ln of y, it's going to turn into the product, and then you use a standard representation of the product into fraction and use L'Hopital's rule. Okay, so that's going to be way number one. Then whatever is your limit, it's actually going to be not the limit of y, but limit of ln of y. So to get y back, you will need to kind of go back to like take e to the power to return back. Way number two, which is basically the same way, just a different representation. Way number two. Represent f of x to the power of g of x as e to the power of ln of f of x multiplied by g of x. What kind of property I'm using here? Remember that any number a can be represented as e to the power of ln of a. What allows us to do this? Cancellation rule. E and ln are inverse functions, so you cancel them. So I just use this. E and ln cancel, and we have f of x to the power of g of x. So basically, that's what we are going to have. And then you work with this product, ln of f multiplied by g of x, which is turning to the ratio, and then eventually calculate the limit, and then you plug in this limit into the power of exponent, and that's going to be your actual final answer. Let me show you how to use this to use this way to calculate L'Hopital's, to apply L'Hopital's rule. Okay, I'm going to consider example, and that's going to be limit of x to the power of x as x approaches 0. Cool. Remember, we use this x to the power of x to explain why do we need logarithmic differentiation. Yeah, we need logarithmic L'Hopital's rule, basically for the same function. So what we have here is 0 to the power of 0. We go back. So we have this case, 0 to the power of 0. I'm going to use way number one. So I'm going to take a ln of both sides. So I'm taking a ln of x to the power of x, and that's going to give me x multiplied by ln of x, right? This x jumps in front. Now I'll need to represent this as a fraction. And remember, never put ln down, right? So I'm going to keep ln numerator and 1 over x in denominator. And now I'm going to see that when x approaches 0, this is infinity. Well, actually negative infinity, right? And x approaches 0, this is infinity. So we do have infinity over infinity. So we are going to use L'Hopital's rule. And I'm going to put now limit over here because kind of I was supposed to write down limit everywhere, but forgot. So derivative of ln is 1 over x, right? Derivative of 1 over x is minus 1 over x squared. X approaches 0. Why do we need to write down limit? Because we need to label somewhere where x goes. And we already had this limit, right? You guys probably remember that when we simplify it, it's going to be a limit of like x was minus as x approaches 0, and that's going to be equal to 0. This 0 is not our answer actually, because what we have over here is a ln of our function. So actually, a ln of y equals to 0. Now, what is y? E to the power, e to the power, e to the power of 0 is 1. So our actual limit is equal to 1. Okay. In case you wish to use way number 2, how it would look like to go. So in our case, x to the power of x, it's e to the power of ln of x. I'm representing this x, bottom one, and multiplied by x. If you look at my expression for which I'm looking for a limit, ln of x by x, it's exactly the same expression. So basically, way number 1 or way number 2 is going to give you same answer. Well, I'm going to skip all these calculations because I did them already and I found the limit. Limit is equal to 0, so it's going to be e to the power of 0. It's not like you can skip it if you kind of do it way number 2. If you do it way number 2, you will need to kind of write this down separately and calculate the limit. But I already did this, so I'm using the result. And of course, the answer is going to be the same no matter like which way do you use. Okay, so that was 0 to the power of 0. Let's consider something more complicated. Example number 2. Limit 1 plus sine of 4x to the power of O tangent of x. Looks like a very crazy limit as x approaches 0 plus. Well, what do we have here, guys? What happens to the sine when x approaches 0 plus? Well, 4x still goes to 0 when x goes to 0, so we have 1 plus something very small, so almost 1, right? Cotangent. Well, guys, if you forgot how cotangent looks, cotangent looks like this, I guess, right? And this is cotangent graph, cotangent of x, and we see that it goes to positive infinity when x approaches 0. So we do have 1, almost 1. If it's just 1, regular 1, it's going to give you just 1. But if it's 1 plus a little small addition extra, can be actually anything. And cotangent goes to infinity, so we have 1 to the power of infinity. Well, here, guys, I'm going to use way number 2 because I already considered something solved way number 1. So I'm going to represent this expression as e to the power of ln of 1 plus sine of 4x. And then the cotangent is going to give me just another power. And that's going to be the limit. Okay. I'm going to bring the limit to the top of exponential function. Why we can do this? Because exponential function is continuous. So the limit of the function is actually just like a number which you get by substituting the limit of the argument. Remember, for continuous function, limit f of x as x approaches a, if f of x is continuous, is just f of a. We are using this fact when we do move limit from the bottom to the top. So we can just find the limit of argument and plug it in here. So what we have e to the power limit of ln of 1 plus 4x, not 4x, sine of 4x, sine of 4x, and multiplied by cotangent of x, and limit as x approaches 0 plus. Now we're going to concentrate on this expression and see if L'Hopital's rule is going to work. I'm going to copy the limit now. Limit ln 1 plus sine of 4x multiplied by cotangent of x. X approaches 0 plus. So what do we have? Well, we are going to have 0 here. So 1 plus 0 is 1. And ln of 1 is equal to 0. So we do have 0. And what happens to cotangent? Cotangent at 0 we already know equals to infinity. And we do have the product of 0 and infinity, which we can turn into a fraction. Well, according to my rule, never put ln down, I'm going to put down cotangent. So limit ln of 1 plus sine of 4x. And here down, what is 1 over cotangent? I'm supposed to write down here 1 over cotangent of x, right? But what is 1 over cotangent? 1 over cotangent is actually tangent, right? So I'm going to erase cotangent and just write down tangent. Oh, very nice, right? We don't have 1 over something. It's just gonna watch. Now let's check what we have in numerator. We have 0. What is tangent of 0? Tangent of 0 is also 0, and we have indeterminate form 0 over 0, where we are going to use L'Hopital's rule and differentiate both parts, numerator and denominator. So I'm going to start with doing derivative of ln of this 1 plus sine of 4x. Well, it's not going to be very short, but we still can have it. So first we differentiate the ln. It's 1 over argument. My argument is complicated, but brief. And I'm going to do it. Now we need to differentiate the argument. So 1 is going to give us 0 derivative of 1. And sine is going to give us what? Cosine of 4x. And the last thing we need to differentiate 4x itself, right? Because it's another composition and we are going to get 4. Denominator is much easier, right? What is derivative of tangent? Everyone's supposed to remember the derivative of tangent is a secant square of x. X approaches 0. Now, guys, I'm thinking that I want probably simplify it a little bit, but maybe I even don't need it. Okay. I'm going to write down instead of secant. Maybe I don't need it. Guys, do you remember that secant at 0 is equal to 1? Cosine at 0 is equal to 1, and secant is 1 over cosine, so it equals to 1. So let me just kind of plug in the numbers now. When x goes to 0, I'm going to write down a limit. And this is 1, right? Cosine of 0, when x equals to 0 is equal to 1. Then multiplied by 4, just because 4 was here. In denominator, 1. The sine of 0 is 0. And in denominator, we remember that secant is equal to 1. Okay? And now I don't think that we need actually x approaches 0 just because there is no x anymore. So I'm just going to erase the limit and calculate the number. So what do we have? We have 1 by 1 by 4, which is 4 divided over 1 over 1. It's going to give us 4. So my limit is actually equal to 4. It's not going to be our final answer. Now what I'll need to do, I'll need to look where I started. So I just calculated this limit, and this limit was equal to 4. So my final answer is going to be e to the power 4. You know, the very typical mistake people are doing in their exams and quizzes, they're forgetting to go back. And it's going to cost you some points eventually. Okay, I think that's all about indeterminate powers. I'm going to put examples like for self-solving, but actually that's all. So let me now put examples which you will need to prepare for Wednesday. Scroll it up. And so guys, I'm going to put some fractions and then some powers. We remember that powers are usually going to result into products. So I think that's going to be like more than enough fractions and powers. So it's problem number 1. Limit ln of x. I think we did this already, ln of x divided over square root of x. I don't want to use the same one. Let's do this. Limit of e to the power of x minus 1 minus x. Yes, I'm going to rewrite it. e to the power of x minus 1 minus x in numerator and x squared in denominator. A little clue here. You will probably need to use L'Hopital's rule twice. Limit number 2. Limit of 1 minus cosine of x over x squared. Here, guys, again, you probably will need to use L'Hopital's rule 2 times to calculate this limit. Problem 3. Limit x to the power of a square root of x. X approaches 0. Maybe I should write down on the right because we do have the square root, right? Number 4. Limit sine of x plus 1 to the power of 1 over x. X approaches 0. I think maybe we should do 0 plus 2 here. And number 5, I'm going to put it here next to limit x to the power of 1 over x. X approaches infinity. Okay, so just 5 limits. For practice. So we do have 2 fractions, and all these powers are going to result into product. So I think that's going to work. Powers and products, as I said. I think that's all about L'Hopital's rule. And of course, you can do more problems, just like when you do the homework. Okay, so that's going to be it, and I'll see you for Wednesday.